Hello dear learners. In today's lecture, we will try to understand aspects related to the structure and photochemistry of Earth's ionosphere. In the past few lectures, we have seen what is ionosphere, how it is formed, which part of the solar radiation is responsible for the formation of ionosphere, different layers of Earth's ionosphere, their day, night, annual, seasonal and solar cycle variability, and the reason why the uh, ionospheric electron density has a particular shape, and how many layers will exist during the daytime and how many layers will exist during the nighttime. Briefly, what is the reason for the disappearance of few of the layers in the nighttime, and at the same time also the reason for the persistence of the E and F layers in the nighttime. We have briefly discussed all those aspects. So, in today's class, we will more or less continue this discussion and learn about few other important aspects about the ionosphere. Right. So, what you see here in this figure is on the x axis you have the number density, which is per centimeter cube, and on the y axis you have the altitude, which is in kilometers. Right. So, the bold thick line that you see here, redrawing it just to distinguish it from the other lines, is the ionospheric electron density profile with respect to height. So, here you are able to see the inflection points clearly, and these inflection points mark the boundaries of the respective D, E, F1 or F2 layers. The peak electron density is usually at 250 to 300 kilometers in the altitude and corresponds to approximately 10 to the power of 12 electrons per unit volume. Right. If this is the electron density, this total electron density should be the sum of all possible positive ion species, O plus. And in the last class itself, we have clearly understood what are the major ionic species, positive ionic species in the lower part of the ionosphere and how it changes to the upper parts of the ionosphere, right. So, we have NO plus molecular ions dominating in the lower ionosphere, O2 plus, etc. Even let us say H plus, all that, right. So, this figure simply shows the variation of ion densities with respect to height. On the other side, this side, we have the neutral density variation with respect to the height, which is more or less an exponential decay with respect to height, right. So, here in the bottommost parts of the ionosphere, the major ionic species are O2 plus, NO plus, okay. And if you go to the higher altitudes, the major ionic species will be O plus, and even at very large altitudes, it will be H plus or He plus, right. So, this equilibrium is called as the photochemical equilibrium, which means the total positive charge density is equal to the electron density. There is a dynamical equilibrium as long as there is direct sunlight, the ionization is constantly happening, and at the same time the recombination is also happening at the same speed. And at any given time, the total number of electrons macroscopically will be equal to the total number of ions in the entirety of the volume. But if you look at the small pockets, there may be chances that there are some small changes or small net charge accumulation, which will be eventually be taken care by the plasma oscillations, right. So, this equilibrium or this state of matter in which the plasma is existing can be called as quasi neutrality. Yeah. So, in addition to the features or basic structure of ionosphere, we have few more very important aspects about the ionosphere. What you see here in the left is an actual measurement based out of the incoherent scatter radar at Arecibo. So, what you see here is the concentration on the x axis, concentration of any species on the x axis, and on the y axis you have the altitude. So, what is being highlighted is this is at very large altitudes, 1000 kilometers or even more than that. You realize that the total electron density is almost compensated entirely by the density of hydrogen ions, H plus. So, above around 1400 kilometers during the daytime and 700 kilometers during the night time, H plus becomes the dominant ion in the upper parts of the thermosphere, forming a layer which is entirely dominated by H plus, right, ionized hydrogen, right. That is why we call it as the protonosphere. So, the topmost layer of the ionosphere above 1400 kilometers during the daytime and 700 kilometers during the night time, the layer of the ionosphere is called as the extension of ionosphere is called as the protonosphere. And at low latitudes, closed magnetic field lines reach out to several Earth radii, forming flux tubes. This region is referred to as the plasmasphere. Okay. So, these are the closed magnetic field lines which are converging and diverging at different poles of the Earth when considered as a magnet. This flux tubes, this region is referred to as the plasmasphere. Right. So, here in this figure, in the second figure, you can clearly see the total electron density is almost equal to the total positive ion density above 1000 kilometers. This minor difference could be because of the other ions which are He plus. So, like I said in the earlier classes, hydrogen being very light tries to escape the Earth's atmosphere, and because of the availability of solar UV photons, it will get ionized and form the H plus ion, right. So, now we know, in addition to the ionosphere, we also know what is the protonosphere and what is the plasmasphere. So, this completes, let us say, our basic knowledge about what is ionosphere, where does it exist, and what is the extension of ionosphere which almost goes and merges with the magnetosphere, right. This is the basic idea. Okay. You have protonosphere, you have plasmasphere, and then you have ionosphere, etc. And we also know at this point of time that how many different types of ions can exist, and out of these ions, which are the ones which will be most populated in the lower altitudes and which will be populated at the higher altitudes. So, there is a distinct difference between the type of positive charge species that you can find at different altitudes. And more importantly, in the solar radiation, as it is traveling into an optically thick medium, it will ionize and produce different types of ions based on what is available. Let us say at the lowermost altitude, molecular neutral densities are more. So, that is why if the solar radiation, extreme ultraviolet radiation or X radiation, which can dissociate molecules or which can ionize molecules itself, if it reaches, then it will produce those ions. So, it is a very simple understanding how the radiation is coming in and how it is ionizing and producing different types of ions, right. Now, most importantly, these different types of ions and the rates with which they recombine and produce neutral states are not the same. That means, if you take a molecular ion and if it comes in contact with an electron and forms a neutral state, the speed at which this recombination reaction will happen or will occur will not be the same to the speed that with which an atomic ion, a O plus, will recombine with an electron. So, these different speeds will only be responsible for the persistence of ionosphere at some altitudes and disappearance of the ionosphere at some other lower altitudes, right. So, intuitively, this is the basic reason why it exists or why it does not exist during the night time. Right. Now, let us look at the distribution of species and what is the importance of scale height in order to understand ionospheric processes. Okay. So, we all know very well that the atmosphere is a thin layer of gases which is surrounding the planet. And why is it surrounding the planet? Why does not it escape just like moon or very small planets? Why does not the atmosphere just escape? Because it is held by the gravitational pull of the earth, and the gravitational pull has to be sufficiently large or it has to be beyond a threshold, only then it will be able to hold the atmosphere. You are holding the atmosphere, so there must, you are obviously talking about some other force which is trying that atmosphere does not get holded by the planet Earth. Or simply put, there is also a force which is acting exactly opposite to the gravity. The force is called as the pressure gradient force, which is equals to minus 1 by rho del P, which means the pressure gradient force is opposite to the gradient of pressure. So, you have the surface of the earth, you have near the surface of the earth, you have the high pressure, and as you go away, you have the low pressure. Why do you have a low pressure there? You imagine a diffused gas, or simply put, the density of the atmospheric species is decreasing exponentially with respect to height. So, as a result, as you go away from the surface, at any point the density will keep on decreasing. So, there is a gradient in the pressure. So, that is why you have a high pressure near the surface and low pressure away from the surface. So, imagine any point. Okay. So, between these 2 points, the pressure gradient is in this direction, right. Gradient defines the direction in which the physical quantity is increasing at its fastest rate, right. So, this is the gradient. So, the force, obviously, even if you do not know all this, you know the simple reason that gas or the fluid has a natural tendency to occupy the volume or move from a point of high pressure towards a point of low pressure. So, the direction of fluid movement should be in this direction. So, the gradient is in one direction and the resulting force because of this gradient is exactly in the opposite direction. That is why we have a minus. So, this is the pressure gradient force. Now, if this pressure gradient force alone were to exist, okay, if it alone were to exist, then it will moving the entire fluid or the entire atmosphere into the higher altitude, and thereby it will simply escape. But then you have another force, which is the restoring force, which is trying to pull the fluid towards the other direction. So, this is one direction in which the fluid is trying to escape, and the same gravitational pull is the one which is trying to hold the fluid. Now, if these two forces are equal, then you get an equilibrium condition, which is called as the hydrostatic equilibrium. So, the reason for the atmosphere to be held by the planet Earth is the gravity, and the resulting equilibrium is called as the hydrostatic equilibrium. These are very basic things. So, I believe you must be knowing all these things. Even if you have some doubts in this, you can refer to earlier lectures, then it will be very clear. So, the hydrostatic equilibrium, if you equate this to the gravity, you will get a simple expression d. So, you have minus 1 by rho dp by dz is equals to z. So, you have that is what you have here. So, the rate at which pressure changes with respect to height is equal to the product of gravity and the density of the fluid, right. Now, this is the hydrostatic equation, and for a perfect gas or for an ideal gas, the gas equation P is equals to nkt, which can be rewritten in terms of density and the mean mass of the molecules. So, if you combine these two equations, so you are combining this with this equation. You can write the density here. Density is equals to pressure times mass divided by nt. That is what is being done here. Thereby, you are getting in this expression there is no pressure in the hydrostatic equation expression. So, you can rewrite the density with the help of the second equation, and then you have pressure which is appearing in the same equation. So, that is why the derivative dp by p is equals to minus the rest of the constants, right, is equals to minus dh dz by h. This parameter g m by kt is equals to 1 by h, or h is equals to kt by mg. So, which is appearing to be a multiplying constant, capital H is k b t by m g. So, temperature at a given altitude can be considered as a constant. Kb, the Boltzmann's constant, is a constant. M is the mean molecular weight. So, if you know the distribution of gases or the percentage concentration of nitrogen, oxygen, etc., M can be calculated, and G is of course a constant. If you substitute the dimensions of each of these constants, you will realize capital H exists in the dimensions of kilometer, right. So, what is this called as? This is called as the scale height. Scale height is a geometric measure of distance by which the density or the pressure decays to its 1 by eth of the value over that particular distance, right. If you make simple substitution, take and integrate this, you will get P of z, pressure at any given height z, is equals to P at the base or the altitude. The lower limit of integration is z naught, the upper limit of integration is z. So, you will get P of z is equals to P of z naught into exponential z minus z naught by capital H. You have defined two different layers, two heights, okay, one z naught, another z. So, P at z is equals to the pressure at z naught times exponential factor of minus z naught, the geometric difference between this in terms of kilometers, divided by a normalizing coefficient or a constant which you call as the capital H, which again exists in kilometers. So, that means this is going to be a number e to the power of minus that whatever number will again be a number, okay, just a constant. Let us say we call it as 2 for example, okay, e to the power of minus whatever is equals to 2. Then the pressure at Z will be smaller than the pressure at Z naught by this factor. This is the essence of the hydrostatic equilibrium. Now, temperature, mean molecular weight, gravity are not functions of Z. We assume it that way. Okay. We know that capital M is constantly changing because wherever you go at higher altitudes, you are going into a diffused gas. So, within unit volume, the total number of atoms and molecules will increasingly become smaller as you travel towards the larger heights. G, of course, G changes with respect to height, but it's not a very fast change. G prime is G into 1 minus 2h by capital R. H is the height at which you want to calculate the gravity. G is the gravity at the surface. R is the radius of the earth. So, you see this, that since you are dividing with a number which is of the order of 6,400 kilometers, right, 6,400 10 to the power of 3 meters, and the heights that we are talking about, even if you consider the entire ionosphere itself, let us say up to 1,000 kilometers, it is still very small in comparison to the normalizing factor. So, the difference in the gravity over those distances will not be much. So, that means you can take G to be a constant. Temperature, of course, you cannot take it to be a constant, but you are referring to ionosphere above, let us say 70 kilometers or even above 90 kilometers, you already crossed the mesosphere. The thermosphere, the temperature steadily increases with respect to the distance. So, you can say that for certain very small distance or layers, you can assume the temperature to be a constant. Then in those conditions, the earlier expression for the pressure can be directly extrapolated for number of neutral species. Okay. And within the 100 kilometers, within the first 100 kilometers, the atmosphere is very well mixed, which means that any unit volume will have ideally be representative of the atmosphere of the earth. It won't be like, it won't be skewed in terms of it won't be different. Okay. And above 100 kilometers, the diffusively separated atmosphere exists where the scale height of each species will be different. Okay. So, each neutral species, let us say nitrogen, will be distributed as per its own scale height. Earlier, we have used capital M to be the mean molecular weight. Here, we are using in the diffusive equilibrium dominated atmosphere, we use the mean molecular weight of the individual species. So, this is how the scale height starts to behave differently in the ionosphere. So, each species has its own scale height. Another important aspect in the ionosphere, which is slightly different from our idea of dealing with a neutral gas, because ionosphere is a plasma state. Plasma, what is plasma? Plasma is the fourth state of matter in which electrons and ions also exist in addition to the neutral species. There are neutral atoms, neutral molecules. In addition to that, significant population of electrons and ions exist. So, how is it going to matter? If charged species are there, this gas that you are talking about, plasma is also a gas. This gas becomes electrodynamically active. So, neutral gas is inert to electric and magnetic fields. Electric and magnetic fields cannot have any effect on the neutral gas, but if it is a plasma, the electric and magnetic fields can influence various aspects about this gas if it is a plasma gas. Okay. So, that is why the ionosphere cannot be treated like a simple or neutral or ideal gas, it has to be treated like a plasma. You have to understand the ionosphere, you can understand the basic aspects that we have been doing for the past 2 or 3 lectures, like just like how does it exist, where does it exist. These simple questions can be answered very easily. But if you want to understand ionospheric dynamics, or how the ionospheric processes change with respect to time. What are the additional factors which can influence parameters related to ionosphere? Then you have to treat it like plasma because it is electrodynamically active. It behaves as if a conducting fluid is moving from one place to another place. Now, right, so if it is a conducting fluid, then we should talk about its conductivity, its collisions, so many things. Right. That discussion eventually starts here. So if it is a neutral gas, what are the parameters that you can think of to describe the state of this neutral gas at any point of time? You will need the pressure, you will need to know the volume of this fluid or gas, you will have the knowledge of temperature and let us say density, the chemical potential, etc. So these are all parameters which are related to the neutral gas, ideal gas. Okay. But when you talk about plasma, in addition to these parameters, you also need to know what is electric field, what is the magnetic field, and how does gas behave in the presence of these fields, what is the conductivity, what is the current density, so many things, right. So this is how the plasma state is different from the ideal gas, right. And more importantly, the temperature, the fundamental idea of temperature is very simple in a neutral gas. It represents the average kinetic energy of the molecules, okay, kinetic energy of the molecules. But in plasma, the kinetic energy, the temperature can be defined separately for electrons, which we call as the electron temperature, ions, which you call as the ion temperature, and for neutrals, you also have a temperature neutral. Right. Ideally, the simple explanation which can describe these three variations of temperatures to exist is that if there are collisions, right. So in neutral gas, what happens? Let us say you consider 10 to the power of 25 atoms or molecules per unit volume. In that case, these atoms or molecules are colliding with each other all the time. So there is a continuous exchange of heat or exchange of energy. Before talking about heat, exchange of energy between the atoms or molecules. So eventually, after a certain point of time, after a very brief period of time, an equilibrium will be reached where number of neutral species and their energies can be represented over a distribution, which simply says maximum number of molecules will have mean energy, minimum number of molecules will have maximum and minimum temperatures. Okay. So this is the distribution. But if you don't allow these species to collide, then you cannot strike this distribution. This distribution of energies is very difficult to achieve. So that's why if it is a very rarefied gas, if the number of atoms are very, very small, then the mean free path of these electrons or ions becomes very, very large. So that means they won't get to collide with another electron or ion for very large distances. So the idea of reaching thermal equilibrium also becomes very, very sparse. So if you look at this figure, this shows the temperature with respect to the altitude. So this is the altitude and this is the temperature. What do you see here? Up to a certain point, the temperatures of electrons, ions and neutrals are the same. So they are following the same trend line. They are increasing as you go away from the surface. But after a point of time, the temperature of electrons steadily increases and then decreases and then steadily increases thereafter. So the rate of temperature increase for electrons is not equal to the rate at which temperature increases for ions. It is a different. So at any given height, you measure these three different temperatures. So the electron temperature will be very, very large, ion temperature will be small, and the neutral temperature will be very, very small in comparison to this. Right. So this difference is only because of the existence or non-existence of the collisions. In the ionosphere, we distinguish between the ion temperature and electron temperatures. Ions and electrons receive thermal energy during the photoionization process. You know what is photoionization, right? So X plus H nu giving you X plus electron. This is the photoionization. So electrons receive thermal energy during photoionization and lose thermal energy through collisions. So since recombination lifetimes are smaller than the timescales for losing excess thermal energy, the ion and electron temperatures above 300 kilometers are both larger than the neutral temperature. Right. So this is the reason that they exist separately, because the lifetimes, the recombination lifetimes are smaller than the timescales for losing the excess energy. recombination lifetime is smaller. So, you need certain amount of time for losing the excess energy. How do you lose the energy? There has to be something with which you can interact and exchange or reach equilibrium, right? So, this process of finding that other atom or molecule will take some time. That depends on the density of the fluid. If it is very dense, it will be immediate. If it is not dense, if it is rarefied, it will take some time. So, there is some characteristic time limit which is required for losing excess thermal energy. This time seems to be larger than the recombination lifetime. So, before it exchanges energy, recombination happens, or the charged state will vanish. Okay. So, this is the reason why the ion and electron temperatures above 300 kilometers are both larger than the neutral temperatures, which is Tn. So, now we see the possibility of having these three temperatures: electron temperature, ion temperature and neutral temperature, right. So, before moving into the few more aspects about the Earth's ionospheric layers, now we will try to discuss what exactly are the different types of ions, how do they exist, what type of chemical reactions are responsible for their appearance or for their disappearance. All these things will be covered in the subsequent lectures.